All right, y'all. So let's talk about solubility rules. This is a little bit more memorization, but I have a trick for you guys to hopefully help you guys later as you kind of start thinking through this. Okay. So solubility, by definition, is the amount of solutes, again, the small stuff that will dissolve in any amount of solvent at a specific temperature. Okay, so the solubility at 25 degrees Celsius is going to be different than 100 degrees Celsius, than 25 degrees Celsius, and all of that. The typical units are moles per liter or grams per milliliter. Sometimes, depending on the field you're in, you'll see maybe milligrams per milliliter, whatever that looks like. But the typical unit you'll see us use is moles per liter, molarity. Okay. Something is soluble if it dissolves in water, and it's insoluble if it doesn't dissolve in water. So then the question is, what does it mean to dissolve? And so for something to be soluble, it's going to form a solution with a concentration that is greater than 0.1 moles per liter. Big M is the same thing as moles per liter, which we saw on the previous slide. Okay, insoluble is going to form a solution that is with a concentration that is less than 0.01 molar or molarity. And then we have stuff that we term partially soluble. So it is kind of soluble, but we can't really say it's insoluble. And those solutions usually form concentrations between the range of 0.1 and or 0.01 and 0.1. Okay, so they fall in there somewhere. They're not above 0.1, so we can't say they're super soluble, but they're not below 0.01, so we can't say they're insoluble either. Okay. So we've talked about double displacement reactions. Hey, two ionic compounds combine and they form stuff. And I had someone ask in class, hey, how do we know if it's solid? How do we know if it's aqueous? How do we know? Up until now, I tell you, hey, this is solid or this is liquid or this is a gas or whatever. But now you can actually predict what you're going to form. Okay. And so you do need to know solubility rules in order for you to predict whether a solution is going to form precipitate. And a precipitate just means a solid or not. Here are the rules. Okay. So in general, so this is the rule. These are the rules. This is the page with the rules. This is all you need to know. You can stop once you're done with this, or you can go on and watch kind of me expand these rules a little bit more. Okay. So nitrate and acetate are always soluble, no exceptions. Okay. Alkali metals, so group 1 metals, 1A, and ammonium compounds are always soluble. So these, no exceptions. Okay, so if it is a nitrate, if the compound has a nitrate in it, or it has an acetate, or has a group 1 metal, or ammonium, always soluble, no exceptions. The next rules are most, with exceptions of usually going back to rules 1 and 2, and then there's some other exceptions. Okay, so most halide salts, so group 7, this is group 7A, are going to be soluble with the exception of silver, lead, and mercury. Okay. Most sulfates, so SO4 2-, so if you have a compound with that, will be soluble with the exception of calcium, strontium, and barium. So if you have barium sulfate, that's not soluble. Calcium sulfate, not soluble. Strontium sulfate, not soluble. Do you see a theme here? They're in group 2A. Okay. Most hydroxides, so OH minuses, are insoluble with the exception of group 1 stuff, right? Rule 1, and ammonium. So ammonium hydroxide is actually soluble because, again, it's soluble. You do have partially soluble hydroxides. You're not responsible for those, but you should know, hey, barium, strontium, and calcium hydroxides are partially soluble. And then everything else is going to be soluble. So these rules are typically for your soluble stuff, a little bit of insoluble stuff. If you see anything else that doesn't fall under here, you can assume it's insoluble. Okay? Technically, we're done. But I'm going to go in a little bit further and kind of talk through these ideas. Okay, so group 1 elements, ammonium, always soluble. Okay, no exceptions. Next, nitrate, acetate, when those combine with compounds, we have them as always soluble as well. No exceptions. Okay. Halides, so chloride, bromide, iodide, when they combine with most things, we assume they're soluble unless it combines with mercury, lead, and silver, then it becomes insoluble. Sulfates are gonna be soluble, typically soluble, unless they combine with barium, silver, and lead. Okay, then they become not really soluble. They are also not soluble with calcium and strontium. Okay, so again, sulfates, group 2, not soluble. Also with lead and silver, they're not soluble. Sulfides are typically not soluble. So anything with the S in it, unless it's combined with group 1 and group 2 elements. Okay, so again, typically not soluble unless they combine with these things. Obviously ammonium, that's always soluble. And then hydroxide, typically insoluble, except, and you should be able to tell me this now, when is hydroxide going to be soluble? Group 1 and ammonia. Okay, then it becomes soluble. It's partially soluble with calcium, strontium, and barium, but like I said, I'm not going to test you on those kind of partial kind of stuff. Carbonate, phosphate, gonna be insoluble unless they combine with group 1 and ammonium. Okay, then they become soluble. All right, I'll go over this in class as well, but NAG-SAG hopefully is gonna help you remember these things. Okay, so NAG-SAG, NAG always soluble. So nitrates, acetates in group 1, always soluble, no question. That's your NAG. The sulfate, the SAG is your sulfate, your ammonium, and your group 17 or 7A. Okay, so sulfates always soluble with the exception of PMS and Castrobare. PMS, lead, mercury, and silver. That's a PM and S. And Castrobare, so Ca, calcium, strontium, barium. Okay, ammonium always soluble as well. And then group 17 would be soluble with the exception of PMS. Lead, mercury, silver. Okay. In general, solubility increases as temperature increases. So I talked about supersaturated solutions where you can force stuff to dissolve if I increase the temperature. That's the idea here. For most ionic substances, when you increase the temperature, you're typically going to increase solubility. For gases, though, when you increase the temperature, you actually decrease the solubility. Think about it. Why is that? If you increase the temperature of the gases, they can move around more. They're going to escape where they're at. So you don't have a lot of gases in solution. They're not going to be soluble. Okay, we'll talk about this a little bit more next class when I actually am in class, I think on Tuesday. But in general, when we write our ionic equations, when we write equations for when things break up, you literally take them and you break it up into their ions. This is why it's important to know what the charges are on those things. And if we're breaking them up in water, we assume they're aqueous. Okay, so this is how these things are going to break up. And remember, you always want whatever you have on one side on the other side. So we always have to make sure that we're dealing with balanced things. Here's another example of that. So I have this compound. When it breaks up in aqueous solution, it breaks up into two things of the ammonium ion and dichromate, one thing of the dichromate ion. Okay, and they're aqueous. Dissociation, ionization reaction. So remember, we talked about dissociation, ionization, as breaking up. The big idea here is ionic things, ionic solids are going to dissociate. Regardless of whether or not they're soluble, they break up completely in solution. So even if a little bit dissolves, so the concentration is very little, the ions in there, everything is an ion. Okay, it breaks up into stuff. Again, don't confuse solubility with dissociation. Just because it breaks up into ions doesn't mean it actually dissolves. Okay, so acetic acid, it's vinegar. Vinegar is actually very soluble in water, as you probably know. Okay, but when you look for how much electricity that conducts, it's actually a very weak electrolyte because it does not break up into ions in solution. Barium hydroxide is actually not very soluble in water, but the little bit that does dissolve in water breaks up completely into ions. So barium hydroxide is actually a very strong electrolyte, even though it's not very soluble in water. So dissociation, solubility, two different things, okay? You can be very soluble and not dissociate completely, and you can dissociate completely but not be very soluble. Okay? In the end.